Okay, so we are happy to invite Professor Rakić from Belgrade University to speak on a model of non-local de Sitter gravity and its solutions.
Thank you. First of all, I want to thank organizers for kind invitation to this meeting. Of course, I want to express my gratitude to Professor Vesnin and Professor Bardakov on their 60th birthdays. Today I will speak about on a model of non-local de Sitter gravity, which was developed by me and my colleagues Ivan Dimitrievich, Branko Dragovic, and Jelena Stankovic. We are working in this subject for several years, and I will show these new results. The lecture will consist from 3 parts. In first part, I will speak very quickly about some introduction to this subject. In second, I will express our results, and in last one, conclusions, which are connected with some harmony between our result and observational data. Let's start. So, general theory of relativity assumes that universe is 4-dimensional, homogeneous, and isotropic pseudo-Riemannian manifold of signature 1, 3. There exist 3 types of homogeneous and isotropic simple connected spaces in dimension 3: sphere of constant positive sectional curvature, flat space of curvature equal to 0, and hyperbolic space of constant negative sectional curvature. Generic metric in these spaces is of the form of Friedman-Robinson-Walker metric, which is given by a very well-known Formula 1. In this metric, very important is this function A of t, which is called cosmic scale factor, which describes the evolution of universe, and parameter k, which describes the curvature of the space. So if k is equal to 0, it is flat space. 1 it is sphere, and if it's -1, it's hyperbolic space. General theory of relativity is based on Einstein-Hilbert action. Maybe it's it means with this action where R is scalar curvature, G is determinant of metric tensor, lambda is cosmological constant, and L of M is Lagrangian of matter. The variation of the action of this action, we obtain a very famous equation of motion, in which T mu is the energy momentum tensor, G is metric, R is Ricci tensor, and I is scalar curvature. The energy momentum tensor for ideal fluid matter in cosmology is given by this diagonal matrix, where rho is energy density and P is pressure. And using the conservation law, we get equation 4. Since in the cosmology we have a equation of state given by this formula, it means that one. And if we solve this equation 4 using this connection, we obtain solution for energy density. The basic types of matter in the universe is cosmic dust when this parameter W is equal to 0, and solution in this case is some constant a to the power minus 3a is this scaling factor. Another one is radiation, which was dominant at the beginning of the universe. And here W is 1/3, and we have that solution. In this moment, the ratio between energy density of ordinary matter, it is like this first one, and radiation is about 10 to the 6th. But at the beginning of universe, this ratio was completely different and opposite. From the expression for Friedman-Roberts Walker metric, it follows that scalar curvature is function of time and given by this formula. And it is possible to using this Friedman equation to obtain these two equations. Here we introduce a very important parameter, which is called Hubble parameter. It's a ratio between derivative of A and A. General theory of relativity it has great success in the following things. So the precision of Mercury perihelion, the bending of light in gravitational fields, the gravitational redshift of light, the gravitational lensing, and many others. But it has also some deficiencies. Those deficiencies in those problems were consequences of very great cosmological observation. First one was high orbital speed of galaxies in clusters, then high orbital speed of stars in spiral galaxies, and accelerated expansion of the universe. Also, one problem is Big Bang, which is singularity in this theory. And general relativity yields cosmological solution with zero size of the universe as its beginning, and what means an infinite matter density. This is a question. And in such situation, it's need to find a solution and modify the vicinity of singularity. There are two natural approaches to modification. First one is dark matter and energy. It means that in Lagrangian we add some parameters, and another one is modification of Einstein theory of gravity. So it means modification of this Lagrangian. First one, dark matter and dark energy. Dark matter is responsible for orbital speeds in galaxies, and dark energy is responsible for accelerated expansion of the universe. If Einstein theory of gravity can be applied to the whole universe, then the universe contains about 5% of ordinary matter, 27% of dark matter, and 68% of dark energy. It means that 95% energy content of the universe represent dark side of the universe, which nature is unknown. Motivation for considering modifications of Einstein theory of gravity is that the validity of general relativity is not confirmed on cosmological scale. Dark matter and dark energy are not yet detected in laboratory experiments. There exist different approaches to modification of Einstein theory of gravity. As I mentioned at the beginning, we have this action and the field equation, which is consequences of these actions. And then first modification were started by Einstein, who put cosmological constant. Then we can see that very early were made the first modifications. We have several types of modification. Essentially, what we do, we replace in this Einstein-Hilbert action scalar curvature by some function of different objects. Here we have cosmological constant, Ricci tensor, scalar tensor, D'Alemberian, and so on. One of the first invariants was Gauss-Bonnet invariant. It is that one which is given by that formula. Then very importantly, FR modified gravity. It means that we scalar curvature in this action replaced by some function of R. Gauss modified gravity is essentially a special case of FR modified gravity, and non-local modified gravity is the most complicated, in which we have several objects here which enter in this function. We mainly work with this modification. We add this term in the action where f of D'Alemberian is an analytic function of D'Alemberian, and lambda is a cosmological constant. As from Friedman-Robertson-Walker metric, it is possible to find the scalar curvature action of D'Alembert operator on R. Here we have this Hubble parameter, which is very important. And this was some kind of general introduction. And now we will say a few words on our approach. First one, our action was complicated and more difficult than the first one. We had this action S1. It means this part which includes just modification. And here we have one technical lemma which we need to find that action. The action S0 is a standard Einstein-Hilbert action without matter. Its variation is this very well known formula is given by formula 6, and using previous lemma and the results from this lemma, we can find finally the variation of this part which we add, and we obtained formula 17. Here we have some non-trivial parts, and if we take so we start with this section, we finally obtain equation of motions. Those equation of motions, so we obtain from left hand side this tensor. It's given by that one, by this formula. Here we have some ingredients. Here lambda mu nu, k mu nu, and so on. And the W, it is clear that this equation is very complicated, and it holds for any metrics. So since we use diagonal metrics, it means Friedman-Robertson-Walker matrix, we will obtain from those 10 equations just 2 of them which are linearly independent. This one is 2 of which is usually used is J00 and trace equation. what is also interesting in this derivation of this of proof of this theorem is that one can replace function j and h and obtain the same equation of motions. Further we consider case when Q R is equal PR. It means here we change a little bit notation. So H and Q are denoted by P and Q. And we take that this function are eigenfunction of corresponding D'Alembert-Beltrami operator. And then if you use this formula, one can conclude easily that something like this holds. And then we obtained, in this case, equation to motion are reduced to formula 9, which looks much easier than in the case when Q of R and P of R are not equal. This last remark I mentioned, so we have just two linearly independent equations, and at the beginning of our work on this subject, we try to find and consider the cases in which those functions are in the following list. So if R is constant, H of R and G of R are equal to R, and so now I will skip these some results which we obtained, since we don't have so much time for this case, and we will consider this last model, in which H of R and G of R are equal to square root of R minus 2 lambda. And also, we started with, as I mentioned before, this calligraphic F include just positive exponents of D'Alemberian operator. In last paper, we add also with negative terms. Why this model is very important? Because it is very special case of this equation, since this equation 9 became much more easier. So it is more simple, since the reason is because product of P and P prime is constant. So finally we obtained such equation 10. So previous equation is reduced to this one, and what we can see from equation 10. From equation 10 we can see that if calligraphic F of Q is equal to -1, and its derivative is equal 0, then we will have a solution. So here we have this factor will be 0, and also here the second one. It's not so complicated to find some function which satisfied this equation, and one of such equation is given by this last formula. So here we see that we have some exponential function. Then we consider corresponding and trying to find not all, but many many of scaling factors in elementary functions. So first, we suppose that that this scaling factor is of that form, and we work in flat space. Then there exist such two solutions. First one is given by this A1, which is by our we think that this is very important solution, and we will discuss them a bit later. And also this solution A2, we see that both of them fulfill these two conditions. So f of minus 3/7 of lambda is equal to -1, and so Q is equal this.
Zoran, please, can you say something about parameters? What is A, what is lambda? Just recall, please.
This A is constant.
It's constant, and lambda?
Lambda is cosmological constant.
Okay.
After this solution, then we change this function scaling factors. So we try to find scaling factor in this form. Here we have that is a linear combination of some a to the lambda t and beta and e to minus lambda t. Here alpha and beta is constant, and lambda is also constant, the gamma is constant. So it's very general solution, but those equations which we obtained, first we start, we try to find a solution of corresponding eigenvalue problem, and it reduces a lot those possibilities, and we obtained that in the case when alpha beta is not equal 0, r is not equal to 2 lambda, and q is not equal 0, we obtain also some solution. Then special solution which are interested when which can obtain from that form are A3 and A4. So we have cosinus hyperbolic of 2 on the 2/3 and sinus hyperbolic. All of solution are of that kind. So this one, it satisfies that in some point f of q is -1, and the derivative in this point is 0. Next family of solution is given by so we search solution in that form with sines and cosine. So it is similar for calculation as previous one, and we obtained also some under some condition, alpha not equal 0, beta is not equal 0. Only possibilities for gamma is also 2/3. Beta if beta is equal to plus minus alpha and so on, we obtained also two type of solution, and also it's possible in the case when alpha or beta is equal to 0, then we can obtain some special solution which is practically of similar kind. As one can see from this, we work in flat universe. We will, but in solution in open and closed universe. Open is when k is equal -1, and closed is if it is equal 1. We also found some solutions. Which we we search solution in that form under some condition. We obtained solution a to the 9, but it was known from earlier consideration, and also we tried to find similar solution of similar form but with different k. and obtain under some condition on these parameters solution a to the 10th and a to the 11th in both cases in the open and closed universe. And now I will say a few things about this solution, which we will consider more deeply. So we obtain some for that solution. We obtained some nice results, which are very close to observational data. So first we found these parameters with this Hubble parameter, second derivative of scaling factor, curvature. So we can see that all of those functions are function of t and lambda. What is very interesting in this formula for curvature, it is that one that, for example, curvature depend on those three terms, but in today's time, so every term has some. We cannot. All of those terms have the similar value, so it means that we cannot neglect some of them. It's very close. It is one interesting thing about the time in which we live. So then we can also found we have a Friedman equation that we can calculate rho bar and p bar, which are analogues of the energy density and pressure of the dark side of the universe, and use the corresponding equation of state. We see from those expressions that parameter WT bar tends to -1 when t goes to infinity, which corresponds to analog of lambda dark energy dominance in the standard cosmological model. So it is the same as in the current standard cosmological model. It means that this non-local gravity model with cosmological solution describes some effects usually attributed to dark energy and dark matter. This solution is invariant under the transformation 2 to -t, and it is singular at cosmic time. Let us recall from the second Friedman equation, which is given by this formula, which can be rewritten in this formula, where this rho is energy tensor in the standard model of cosmology. Then we can rewrite this equation in this case and divide it by h0 squared. This formula shows practically energy content of the universe. This first term is something. It is a part which belongs to radiation. Second one is ordinary matter. This last one is to the to geometry. It depends of this parameter k, and last one is to cosmological constant. It is we live in this when this last part is dominating. Observational data obtained by Planck for lambda, it is a standard model of cosmology. Is those parameters are given here. It is age of Hubble parameter, matter density parameter, density parameter of this omega lambda, and this pressure of energy and energy density. It is about -1. So from our equation, we taking at h1 and t0 is h to t0, we can find lambda 1 And we obtained this lambda in green lights, in green color. That differs from standard model. We can see that this is very good agreement about the 7%. We also found, we also computed some another important things, replacing solution with k equals 0 in Friedman equation. We can what we want. We want to find some to estimate to give some estimate of different part of terms in that equation, this one, for our model, and compare it with the standard model. So here we calculate some this row difference between our model and so in red color is data obtained by lambda by this standard model, and in green that one which we obtained. Critical energy density is given by this formula, and then we can see parameters which we obtained in our model, and this one obtained by standard model. And we have this. If we compare this, we can see that that we obtain some very interesting parameters. What is here? What is the difference? It is difference is that in our model, ordinary matter, it means this 5%, and dark matter are together. So this is what we obtain essentially. So here those things are here written. We also find some another parameters from our formulas. We find the effective pressure. At the beginning it was bigger than 0. Then decreases and equals at 0 at this time. Also we have this parameter W for our model is also tends to -1, and also we found when from those formula when the Hubble parameter has minimum, and since we know that in one period, in one moment after big inflation, this system, this parameter was not so big. So this is more or less what I want to say. Here are a list of paper which we used in preparation of this lecture. So that's all. So if you have any questions. Thanks for your attention. So we have this, only that one.
Okay. So I would like to ask about the sitter space. So it was in the title, something about the sitter.
Yes.
Where it appear in your consideration?
The sitter means that we have some exponential function times this matrix. So we have here our scaling factor in many parameters includes the sitter. So it means when this parameter is equal some exponential function. Because we use more complicated Lagrangian, we obtained that we can a little bit replace this solution by that one. We have some addition here. So you know, for example, this A2 is second type. I mean, it is similar like the sitter, but here we have T2 squared, which is kind of, this function is a little bit modified. It's not classical de Sitter, but it's some kind of modification. Now we are working, trying to find Schwarz's type of solution. So, but it is a little bit complicated than this. We found a solution in the form of a series, but and have some problems to find radius of convergence of this series. So, but you know, it's normal to, when you add something new, that situation solution will be different.
Okay, thank you. I just expected, so maybe we will discuss de Sitter spaces. So there are hyperbolic space and also de Sitter space and anti-de Sitter space. This is about behavior function. Okay.
Yes.
Okay. And which space is better for the model? I mean, positive curvature or zero curvature or negative curvature?
So I think that this model with the scaling factor of that form, I didn't mention here, we also tried to find a solution for many others, let's say, elementary function, tangent, hyperbolicus, and tangents, cotangents, and so, but we didn't obtain solution. So there is no such solution of this equation. It was not mentioned here. Now so this model, it's somehow very good. I mentioned because it is a very special model, since equation of motion are the most simple. So if you take those functions which enter into Lagrangians are the same, then equation of motion became simpler. But between that one with this square root is the most simple.
Okay. Thank you.
Thank you.
Any other questions? Should we use? Thank you, Professor. So we'll start in about a minute then, the next talk.
The just is to thank the speaker. Thank you very much.
Thanks. Thank you.
Very interesting.